started. Lots of things to talk about today. So this week in lab, we've already kind of previewed this a little bit. We will be doing experiment 8, your Grignard reaction. Lots of steps involved and things that you need to be very careful with. So make sure you read it very carefully and know what you're doing before you come to lab. You have a quiz this week. Bring calculators, good idea for that. Your experiment 6 is report. Experiment 6 report is due this week in lab, so make sure that you have that ready to go. Next week, if you want to get ahead on things for pre-lab, on our schedule it says we have experiment 10 and experiment 11. The actual doing will be experiment 11, and you'll use your product from this week for experiment 11. So if you do want to get ahead, what you will pre-lab is experiment 11, experiment 10 gives you information about GC, which we will cover next week. Your experiment 7 report is also due next week, so make sure that you have all of the information that you need for that, including collecting your mass and your IR spectrum of your final product. So on those lines, up here on the overhead, I have our standard IR spectrum for polystyrene. This is posted on Moodle. You do not need to copy the IR spectrum. It is, everybody has the same standard IR spectrum, so we don't need 130 copies of it. What you do need to do is compare your IR spectrum to that in words, discuss what yours looks versus what that looks like. And then I've given you a peak list. Make sure you include that peak list in your table for your IR spectrum in your notebook for your report, okay? But you do not need to print a copy and put it in your notebook. You just need the peak list and then compare it to your IR spectrum. Also next week is registration for spring semester. So, a couple things to consider if you are taking Chem 256 or second semester organic chem lab. You can register for a 1 credit or 2 credit option. It also says you can register for 0 credits, but 0 credits won't get you anywhere. So you want to register for 1 credit or 2 credits. The semester is broken up into 2 pieces basically. The first half of the semester is much like this part of the this semester. You will be doing experiments out of your lab manual, more in-depth, more involved experiments, but same idea as what you followed here. More experiments out of your lab manual, write reports, so on and so forth, analyze data, things like that. If you choose to continue on for the second half of the semester, so if you take the class for 1 credit, you will stop at midterm and be done with organic lab. If you choose to take the lab for the second half of the semester, you will be proposing a 3-step synthesis and do an independent project. So you will propose the 3-step synthesis and work to complete that 3-step synthesis over the course of the second half of the semester. Okay, primarily the doing in lab part of the synthesis will be after spring break for 5 weeks, and you will make create a proposal before spring break. So reasons to do this would be if you want to try research. It is a very true research-like experience. Most students end up doing a research project from someone's research group. So to try do a research-like experience, if you are a chemistry major, specifically probably a BS major, you would want to probably do the 2nd credit. But even if you are getting a BA in chemistry, after organic chemistry, if you complete the second semester for 2 credits, you don't have to do any more lab hours. So that would be a reason for the BA. You wouldn't have to do any more lab hours beyond that. But if you are a BS, you definitely want to consider it. If you're an ACS major, you really definitely want to take on the 2nd credit. But also if you are interested in testing out research and want to test it out in a small portion, and gain more experience, or want to test it out in the small portion and then continue on, it would definitely be a good option for you to take the 2nd credit. So when you are registering, register for what you think you are going to go for next semester, whether 1 credit or 2 credits, okay? Now, it doesn't have to be set in stone. We can change it once you register. If you decide you register for 1 credit and want 2 credits, we can change it, or you register for 2 credits and want to change it to 1 credit, we can. The one thing to be careful of is if you're at that 16 credit mark, whether or not that will change whether you owe money or not. Okay, so just be aware of that, because anything above 16 credits you will have to pay more for. So if you don't have more than 16 credits now when you register, but then go to change your mind, you will have to make sure everything works out with the registrar's office. But as far as we are concerned, it is okay if you change your mind. It's just helpful to have your best guess for figuring out lab sections, what you want to do. The other thing is, the lab sections, the enrollment are set intentionally low. And the reason for that is so that I can get people into the lab sections that they need. So if the lab section that you need per your schedule is full when you go to register, get yourself on the wait list of the courses that you need. Then you also need to send me an email and let me know what you need, why you need that class. So it's not the want, it's the need is what I'm going to work with. Let me know why you need that particular lab section, and also let me know, because we can't tell this from wait lists, if you are planning on taking the lab for 1 credit or for 2 credits, okay? So if you can't get in the lab section that you need, make sure you get yourself on the wait list. I can't help you get in during the wait list period if you are not on a wait list. If you end up on a wait list, email me your need or needs. So if there's multiple lab sections that will work, let me know, and how many credits you're planning on taking the lab for, okay? And so this will all take place next week, but make sure that you communicate with me, because I am the one who will finally decide what happens with registration and where wait lists are handled and so on and so forth, okay? All right, and also if, I mentioned this last week, if you are in a Thursday lab section attending the Medical Missions Conference, that's not this week, but next week, and you will miss your Thursday lab, we need to get you into a Tuesday lab. So if you have not already spoken to me, you need to speak to me right after lab lecture today if that situation pertains to you. If you're going and you're in a Tuesday lab, it doesn't matter because you will complete your Tuesday lab before you go. But if you're in a Thursday lab and going, we need to get you into a Tuesday lab, because the lab we're doing next week can't be done in open lab. Okay. All right, so let's look at Experiment 8 and all the fun that is going to be involved this week. So Experiment 8, we are going to complete a Grignard reaction, which is not something that is typically taken on in a sophomore level, especially first semester sophomore level organic lab. So feel privileged that you get to participate in this. So our reaction is named Grignard for a reason. Victor Grignard discovered this reaction in 1900. He won a Nobel Prize for it. And so the beginning of this reaction involves, we need to first form what is called the Grignard reagent. And so our Grignard reagent involves organometallic chemistry. So another thing that isn't necessarily always taken on in sophomore organic lab. And what we are making is an organomagnesium halide. So the specific metal involved with the Grignard reactions is magnesium. And so in general, we'll take an alkyl halide, or you could use an aryl halide. We're going to use an alkyl halide. React it with magnesium. We're using ether as our solvent, and we'll talk about here in a little bit why that is. Typically, Grignard reactions take place in either diethyl ether or THF. And we make this species. So it doesn't look so hard so far here. This is our Grignard reagent. And so the important part of our Grignard reagent is the partial charge due to that magnesium that ends up on the carbon that the magnesium is attached to. So magnesium is a metal. It's usually going to take on positive charge. So our carbon has a partial negative charge. So it is going to act in our Grignard reagent. This carbon is going to act as a nucleophile, which does not happen very often that carbon's going to act as a nucleophile. And so if we had an example here, if we had bromobutane, we react it with magnesium in the presence of ether as our solvent. This would be our Grignard reagent. And so here, and this guy is our organometallic compound because we've got our metal, we've got our organic part of it. And this reaction is really important in organic synthesis because of this nucleophilic nature of this carbon, we can make carbon-carbon bond, or we can complete carbon-carbon bond formation, which it doesn't happen very often in organic chemistry. So we do have reactions that work really well. It is utilized quite often. So the Grignard reaction is used all the time because of that. Now this nucleophile can react with weak bases. So it could react with things like water, which is important to keep in mind for here in a little bit. It could react with alcohols. It could react with carboxylic acids, which even though they're acidic, they themselves are very weak bases. We could react with amines. And so the scope of this reaction is really important in organic chemistry, and it being an organometallic reaction is very important. Now, the reason that we use ether or tetrahydrofuran is because it can coordinate. So through the oxygen, it can coordinate with the magnesium. And so that's what helps solubilize that magnesium is the coordination. So you have the magnesium that's just surrounded by ether molecules that help solubilize the magnesium so it can react. Now the other thing with ether, which we know from experiment 3, is it's very volatile, which is good for this reaction because that volatility means that there's a lot of ether vapor that builds up and will keep oxygen out of your reaction. And in a minute here we'll talk about how oxygen can kill your reaction, so we want to keep the oxygen out. Same with THF. It's very volatile, has a high vapor pressure, helps to keep the oxygen out of the reaction. So the solvent choice in the Grignard reactions is really key to the success of the reactions as well. So some side reactions that we need to keep in mind with our Grignard reagent. And things we have to do to prevent these side reactions. First of all, we talked about our Grignard reagent can react with water. Well, if it reacts with water, it will kill the reaction. There's enough water just in the atmosphere to kill your Grignard reaction. So we have to be really careful to keep things as dry as possible. So what happens when it reacts with water, got our nice Grignard reagent, we get our alkyl, the alkane from our alkyl group formed. So we get RH. And then we get bromomagnesium hydroxide that forms as well. So we have now killed our Grignard reagent. It now is no longer useful in the Grignard reaction. So things we're going to do to take care of this. We're going to dry our glassware. We use dry reagents. So the ether is dry specifically, and we keep everything else as dry as possible. So you need to think about this when you are yourself carrying out the reaction. We do not want any water in this reaction until we get to where we quench the reaction. So you have to keep all water away from this reaction. Even when you're setting up your condenser, a leaky condenser can be a problem. Any traces of water you have to keep out of the reaction. So we had you guys get the glassware that you needed together last week, and we're going to stick it in the oven this week. So the morning labs at 7:15, we're going to start sticking glassware in the oven, and the afternoon labs between 12:30 and 12:45, depending on what your instructor told you, you're going to be sticking your glassware in the oven, and we need to dry it at above the boiling point of water to get all the water out, to vaporize the water. So we need to dry it at about 110 degrees or higher for 20 to 30 minutes to make sure we get all the moisture out. So make sure in putting your glassware in the oven, there is no water in it when you put it in the oven, because 20 to 30 minutes is not long enough to completely dry it out. 20-30 minutes is long enough to get the residual water off the glassware that you can't even see, the vapor that just builds up on the glass. But any visual water cannot go in the oven, because then everyone's glassware will not be dry, okay? So if you have questions with that, see your instructor. Next side reaction. We don't want any oxygen in our reaction. So we have our Grignard reagent. We react it with oxygen. What we get is this species, which again kills our Grignard reagent. We don't want that species, okay? We're going to get something very similar to it, but we don't want this guy yet, all right? And so we're going to, we're using ether as a solvent to help keep out the oxygen. You're also going to put cotton balls in all of the openings of your glassware when you get it out of the oven to keep it dry and oxygen out. And in a minute here, I'll show you with the setup, we're even going to keep a couple of those cotton balls in the glassware itself when you're setting up your apparatus, okay? So we're going to keep oxygen out as much as possible. We don't want any oxygen flowing through that reaction. The last thing that we have to be careful of is our alkyl bromide. We're going to add this guy dropwise. And so if we have our Grignard reaction, and we have it reacting with our alkyl bromide, if we add it too quickly, you're going to get an alkyl bromide reacting with an alkyl bromide. So like in our bromobutane case, butane and butane would react together to make octane, which is not what we want. And then you get magnesium bromide. So to prevent this one, we're going to add our alkyl bromide dropwise in a controlled fashion, so we don't get a high concentration of alkyl bromide in the presence of our already formed Grignard reagent. So we basically want this to form as this is added, and we don't want a lot of buildup of this. Okay, so we're going to add our Grignard reagent dropwise so we don't have a lot of concentration of it along with already formed Grignard reagent to react with each other. We just want it to directly react with the magnesium to form your Grignard reagent. Okay? So all of these things we have to take into account with our reaction. So a couple of these things we can take care of with the setup that we're going to use. So this guy is in your lab manual. We also have demos of it in the lab. So here's all the pieces that are going into the oven. And then when we pull them out of the oven, we need to be really careful doing it. We will probably do it in some sort of assembly line fashion. So using gloves, we will carefully pull pieces of glassware out so we don't burn any fingers. Also, so we don't have any glassware dropping and breaking too after it's just been nicely dried, okay? So glassware coming out of the oven needs to do so very carefully, and probably your instructor is going to monitor that situation or take control of that situation. Once you have your glassware, any opening that's open, you're going to stuff cotton in it, okay? And then once it is cooled enough, or you can use your glass stoppers once you have them with a little bit of grease. Once it is cooled enough that you can handle the glassware, this is what you want to assemble, okay? And so you're going to have your stir plate on your ring stand. You're going to assemble your 3-neck flask above your stir plate. And you want to leave probably a good 3-4 inches between your stir plate and that round bottom flask, okay? Now I'll explain here in a little bit why. You're going to clamp that 3-neck flask. Then make sure there's no cotton in either of these joints. You're going to attach your condenser, leave a piece of cotton up here at the top of the condenser. You're going to put your separatory funnel together, attach your separatory funnel, make sure, now remember the stopcock pieces did not go in the oven, so now you need to put those pieces back in. Make sure you then turn it so your stopcock is closed before you put anything in it, okay? Cotton in the top here, a glass stopper on this side with a little bit of grease, and then you're going to have a support clamp here in your apparatus, okay? And then you'll have hoses for water in and water out of your condenser. What you are going to start with is you're going to have your stir bar in here that you should have had when you were heating the round bottom flask. You're then going to weigh out the magnesium. Now you have to be very, very, very careful with the magnesium because it builds up oxides on the outside of it when it is exposed to oxygen, and then that will make it so it won't want to react and form your Grignard reagent, okay? So minimize its contact with oxygen, meaning weigh it out right when you're ready to stick it in your round bottom flask, and stick it in your round bottom flask, okay? And any little pieces of magnesium that end up lying around, let's collect those. We actually have to destroy those little pieces. We can't just throw away the magnesium, okay? But weigh it out right when you're ready to use it and put it directly into your round bottom flask. The other thing that you will have in the bottom of your round bottom flask is 10 milliliters of dry ether, so not red can ether. The dry ether is in the reagent hoods. So make sure you read labels carefully. There's lots of things in that reagent hood, and put 10 milliliters of dry ether in here. Then over here, you are going to make the solution of your alkyl bromide. And your lab manual tells you you need 0.1 moles of your alkyl bromide in 40 milliliters of dry ether. Okay? So you have to calculate that out because everybody's got a different alkyl bromide. Your alkyl bromides are liquids, so calculate the amount you need in volume, not in mass. What is useful is to have the volume, not to have the mass, okay? But you need 0.1 moles, here, make it so it doesn't look like molarity, mole, in 40 milliliters of dry ether. So what you want to do to make that solution is, once you have your alkyl bromide that you need and your dry ether, with the stopcock closed, carefully pour the ether into your separatory funnel, then carefully pour your alkyl bromide into the separatory funnel. The alkyl bromide's more dense than the ether, so it just passing through the ether will make a solution of alkyl bromide, okay? At this point, so you have magnesium and ether, you have ether and alkyl bromide, and nothing has been added to the ether and magnesium. You will have your lab instructor check your reaction, okay? So this is the point where your apparatus needs to be checked, right at this point, all right? And then they will help you add your 5 milliliter portion, add iodine, get your reaction initiated, okay? But at this point right here is where everything needs to be checked. So don't start adding until you have had your reaction checked, all right? Now where that space comes into play is as your reaction is going, if you need to add a little bit of heat to get that reaction going, we know that ether boils at a relatively low temperature. Well, for this reaction, just your hands are enough heat under that reaction to get it going, okay? So we need to leave a little bit of space so you can get your hands under there. Also, eventually, we're going to need to put a water pan under here, so you need to leave space to do that. You will probably want a pan of ice bath in case this gets going too much available, so have that ready to go as well, okay? So you're going to add this reaction mixture drop-wise, and you want to add about 5 milliliters, and then we're going to want to make sure that this reaction gets going. And so what you're going to see is on the actual pieces of magnesium, you're going to see bubbling, and you're going to start to see discoloration in your reaction. You're going to start seeing the dispersing of the iodine color and cloudiness. That is your cue that your reaction has started. At that point, you want to add your alkyl bromide to the reaction such that you keep it refluxing, but you don't want it adding so fast that it's really refluxing out of control, okay? So it's kind of a fine line. You want to keep it refluxing, but you don't want to add it all at once. You don't want to add it too quickly, okay? So as you're going, if you have questions, let us know. Big key here is getting this reaction initiated, okay? We want to make sure we don't have too much alkyl bromide in here for when you get that reaction started. And then we need to keep it going, okay? We don't want the reflux dying out. If the reflux dies out, then we have to get it started again, and it's really hard to get it going again, okay? So you want it initiated, reflux to keep going, but not too crazy, all right? Now, with that, what do you need to remember with ether? What do you need to be really careful of? It's high, it has a high vapor pressure. Also, what do you need to be aware of? It's really flammable, right? Okay. So our alkyl bromide going into this reaction is a very exothermic reaction. So that is part of why we need to make sure that we don't get things going too out of control, because we now have a very flammable situation, okay? We've also talked about why you don't want all your alkyl bromide added at once, because you're not going to get out of it what you want, okay? So you need to control it for the reaction's sake, but also for safety's sake, keep things under control, okay? When you are done with this addition, you're going to heat So we're going to heat the reaction flask in warm water, and ideally try and keep that reflux going. Or if the reflux is still going, just keep it going for an additional 15 minutes, for 15 minutes. Okay? Now, have I said anything about stirring at this point? No. So you will not. So do not stir, okay? This whole time, we have not turned on our stir bar, all right? So do not turn on your stir bar through this whole process of the Grignard formation. The stirring will bring in oxygen and moisture from the air that will kill your Grignard reaction, okay? So we don't want that to happen. So no stirring during the Grignard reagent formation, all right? Once we have heated the reaction flask in warm water for 15 minutes after we added all the alkyl bromide, that is the end of the portion that we're going to call our Grignard reagent formation, okay? And so then the next part is then the actual Grignard reaction, okay? So we've got our nice Grignard reagent now formed. We're not doing anything to isolate it. It's just going to be in your reaction flask. We're going to react this guy now with an aldehyde. And so you all have specific aldehydes that you are going to use for this part of the reaction. Now we've talked about how the carbon here adjacent to this magnesium is a nucleophile. So what would it want to attack of the aldehyde, or where would it want to react at the aldehyde? It wants to react at the carbonyl-carbon, right? Because we're slightly nucleophilic here, slightly electrophilic here. You're going to want that type of reaction, right? And this, again, is something you usually don't see. You don't usually see, except for in this case, a carbon attacking the carbonyl. But it's because partial negative charge here and the partial positive charge there. Again, we are in ether. Haven't changed anything there. And so once this takes place, we get this tetrahedral intermediate. And we get the coordination. This oxygen actually then is coordinated with magnesium bromide. So we've got now partial negative charge on our oxygen, which makes sense, partial positive charge on our magnesium. So if we stop here, this is what we would have. We wouldn't have our final alcohol product that we want. So what we have to do then is acidify the reaction, and we have to quench. This is the quench of our reaction where we will get our alcohol out. So we've got that kind of arrow shift here will form our alcohol. And this is the final product that we want, okay? Now, one thing you have to be careful of is we're going to generate some heat in this quench. And what we don't want to have happen, so we've got acid present and some heat. We don't want the elimination. We want it next week, but we don't want it this week. So you need to control the heat of this quench to make sure that you don't get it going too hot. So if your reaction is refluxing while you're adding the sulfuric acid to quench your reaction, that's too much heat, okay? You don't want anything refluxing while you're quenching with the acid, because you could be potentially doing the elimination reaction and forming the alkene instead of stopping at the alcohol. So to start with this reaction, we've in the reaction flask, we've made our Grignard reagent. We're going to cool. We were just heating in warm water for 15 minutes. Now we're going to cool the reaction in a cold water bath. So it's not an ice bath. That would be too cold. We just want a cold water bath. Okay? You can maybe float a few ice cubes in it, but we really don't want it ice cold. Okay? Now we've got our, so we've emptied everything out of our separatory funnel. All our alkyl bromide is out of there. Close our stopcock. We need our separatory funnel again. Your aldehyde solution is already made up for you. So you just need to dispense 25 milliliters of the correct aldehyde solution. Make sure you read the label correctly. What is prepared is only enough for your class or the class, your class and the class after it if you're in the morning lab. So make sure you read correctly and get the right aldehyde. Also with the alkyl bromide, make sure you read correctly and get the right alkyl bromide. If you don't make the right products, we probably won't have GC standards to help you analyze your product, okay? So you all are going to make a specific set of products that we will analyze by GC, but you need to make the right thing. So read labels very carefully. Aldehyde solution goes in here with the stopcock closed, okay? At this point, this is when we can start stirring, okay? So we have not stirred up to this point. We can now start stirring. You're going to add the aldehyde dropwise. Okay? And again, we need to control the rate of the addition. We don't want things going too quickly. We don't want refluxing out of control. We do want to add this aldehyde dropwise. Another thing you may hear is the actual reaction kind of like spurting at you, or kind of like just making these spurting noises. That is the reaction taking place. So don't be surprised if all of a sudden your reaction starts talking to you, okay? Some of them, depending on the combination, will actually kind of make this spurting noise. But do control this addition. We are adding it dropwise, okay? If you add the aldehyde too quickly, what you will get instead of your alcohol will convert to the corresponding ketone, and we don't want any ketone at all, okay? So even next week, we really don't want any ketone. We'll all probably get a little bit in there, but you don't want your main product to be ketone, okay? So control this aldehyde addition so you don't get the corresponding ketone form. Then, after your dropwise addition, then you're going to stir the reaction at room temperature for 15 minutes. So we still haven't gotten to the quench. We have just added the aldehyde. During this 15-minute stir, get this solution ready, okay? So you're going to need to prepare your sulfuric acid solution. And there are instructions in your lab manual. You are starting with 9 molar sulfuric acid, okay? So that is just half. Concentrated sulfuric acid, 18 molar. You're starting with 9 molar. So it's not really that much more dilute. It's still pretty concentrated. So be careful with it. Wear gloves, okay? Don't get it on you. If any is spilled, get the spill cleaned up. We don't want anyone else setting their hands in it, okay? I would probably throughout this reaction sequence wear gloves. The aldehydes themselves are pretty stinky. You don't want any of those on you. You'll stink pretty bad, especially if you have your butyrylaldehyde. So wear gloves with your aldehyde, wear gloves when you're handling your alkyl bromide, wear gloves when you're handling the sulfuric acid, okay? So you're gonna make this solution. This solution is going back in your separatory funnel, okay? So we've added all the aldehyde solution. Close the stopcock again. Now your sulfuric acid solution is going into that separatory funnel, and we're going to add it dropwise, okay? This time, you're going to cool in an ice bath. So we do want this one cold. And we don't want any refluxing, okay? So if you see ether refluxing, it's gotten too hot. You're probably making alkene. So cool in an ice bath. You're going to add your sulfuric acid solution that you made up dropwise. You're probably going to see any residual magnesium that you have reacting with it. You may see H2 gas being given off as it's reacting. But do keep control of this quench. A lot of times people get to this point and think, oh, I've made it, and then they go too quickly with this part. You've got to be just as careful with this guy as you've been all the way through, okay? Now we have made up a solution with water. So now we are adding water to reaction. So at this point, it is okay that water is going in the reaction during the quench, all right? So finally at this point, if water got in here, it's okay. Any time before this would have been too soon. So there's some reactions that are taking place during this quench. So the first of all, what we want to have happen is we have our species from our Grignard actual synthesis. So we want this guy converted to the alcohol. So we've got that going on. Alcohol is formed. As we make this magnesium MgBr plus, that plus will eventually end up quenched. But here's where we're making our alcohol. So first thing we want to have happen. If we have any Grignard reagent that has not been used up. If you add H plus to that, we are going to kill our Grignard reagent and form the corresponding alkane. And then MgBr plus. We also are killing our magnesium. So the magnesium reacting with sulfuric acid is going to make magnesium sulfate, which is a white solid, and then gives off hydrogen gas. Okay, so you'll see the magnesium reacting, he'll kind of whirl around in the flask, and then hydrogen gas will be given off. During this process, like I said, this is a white solid, okay? So when you get to the end of the quench, and wait till the end because you'll go through different phases of white solid. But once you have added all of the sulfuric acid, if you still have white solid in there, then we need to add a little bit of water to dissolve it before you put it into your separatory funnel, okay? So at this point, if you have any white solid left after you've added all that sulfuric acid, make sure you add a little bit of water, make sure all the solid is dissolved. If you don't dissolve the solid when you put it in your separatory funnel, it's going to clog the separatory funnel, okay? The other thing is after all your sulfuric acid has reacted, if you still have magnesium floated around that never reacted, as you pour this solution into your separatory funnel, we'll want to pour it through some glass wool through a funnel to trap that magnesium. Okay, so if you have questions, if you have remaining magnesium, let us know. We will take a look. Or if you're concerned about whether your magnesium's done reacting or not, let us know. We'll take a look. A lot of times it does take a little bit for that magnesium to react. Okay? And so you're going into a separatory funnel. You're going to separate your layers. What should be on top? What should be in the top layer? Should be the organic layer, right? We're in ether. That's a lot less dense than water, okay? So you're going to separate your layers. Now, we're going to talk about some terminology when it comes to workup and doing aqueous workups that you need to keep in mind because these words are going to keep coming up, okay? So, we've got our aqueous layer. And we've got our organic layer. And to help you out in your lab manual, the flow chart for this reaction is drawn in your lab manual. So you can use that flow chart for this experiment, okay? So this guy is your flow chart. You can draw this from your lab manual, okay? So we've gone through here. We filtered off any magnesium solid. We now have the separation of aqueous layer and organic layer, okay? We're going to take the aqueous layer, and what we are going to do is what is called extract the aqueous layer. With ether. And this is red can ether now. We don't have to use dry ether. Okay, so what it means by extracting, we're taking the product we want out of that aqueous layer and going to dissolve it into the solvent that the rest of our product is dissolved in. Okay, so you're going to extract the aqueous layer with ether. So your organic layer after this, you'll have a separation of layers again. Organic layer goes with organic layer. Aqueous layer remains by itself as aqueous layer, okay? Then you're going to take that combined organic layer and you're going to do what is called wash the organic layer, okay? Now when we wash, we're removing things away from the product layer that we have all our product in, okay? So the extracting is getting more product out of the layer we don't want to keep. Washing is getting things away from that organic layer like salts and so forth that we don't want in there, okay? And we're going to wash with water. and sorry, actually, in this case, not water, we want to use bicarb. Because we want to make sure things aren't acidic anymore. So we want to get rid of all the acid so we still don't have potential for the elimination reaction. Okay? And so there's 5% sodium bicarbonate solution in the reagent hoods. So then, after this part, we are going to get to something else we haven't used before. We've got our organic layer. We're now going to dry it with magnesium sulfate. Which is not the magnesium sulfate we made in our quench, but anhydrous magnesium sulfate. So we're going to dry the organic layer with a drying agent. And these drying agents, usually it is either magnesium sulfate or sodium sulfate. In this case, we are going to use magnesium sulfate. Okay? And so the magnesium sulfate is anhydrous. Okay? There's no water in it. And it's this light, fluffy powder. It looks like flour. And so you're going to have your organic layer. Usually you want your organic layer in an Erlenmeyer flask. It allows less evaporation of your solvent, so it's better to dry in an Erlenmeyer flask than a beaker. And your lab manual tells you to add 1 to 2 grams of magnesium sulfate to it. Now, weight is not, we don't care how much our magnesium sulfate weighs. What we care about is adding enough to dry it, but not too much. Okay, so the weight of the magnesium sulfate does not matter. It's whether or not the solution is dry. Okay, so what happens is the magnesium sulfate reacts with water and complexes with it. And forms this hydrated complex. This is a light white powder like flour. This is more like white, or depending on the color of your solution, colored solid clumps. So what will happen is as it dries, the magnesium goes from this light powder to these clumps that are formed. Okay? And so how you know that you have enough is you want clumps with a little bit that is free floating, or this powder in there. If you have a little bit of powder, you know you have enough. If you only have clumps, then you don't have enough in there to keep drying. If all you have is powder and a lot of it, then you have too much. Okay? So the thing to be careful of here is get enough in there, but don't put so much in there you make pancake batter. It's really easy to add too much and have all your solvent swelled up with magnesium sulfate, and you make this thick slurry. It shouldn't be a slurry. It should be liquid with some free-floating solid with some clumps in it. So when you swirl it around, what it should look like is a snow globe, okay, with a little bit of clumps left. You let it dry. You let it sit 5 to 10 minutes covered. You're going to filter it with gravity filtration. Okay? And make sure you rinse with ether to make sure you get all of your product is a liquid. Make sure you get all your liquid rinsed out. The filter paper with the magnesium sulfate, let it air dry in the back of your hood, and then there is a waste container in the reagent hood for filter paper and magnesium sulfate. Okay? Then what we need to do is a simple distillation. We need to remove our ether. You have to get to this point this week. So if you do not get to the simple distillation this week, you have to do it in open lab. You have to, when you come to lab next week, have the simple distillation completed. Okay? So you're going to simply distill your whole reaction mixture. Remember, we've dried it now. We don't want any water in it. Okay, so once you dry it, keep it dry. Do the simple distillation. Then you will have your crude reaction mixture. We also need to purify that reaction mixture, so we'll then do a second fractional distillation with your all-in-one simple distillation apparatus. To collect pure fractions of your pure alcohol. Okay? For this part, know the boiling point of your alcohol. A lot of times these alcohols are reported with boiling points that were collected under vacuum. So they'll say X boiling point 20 millimeters of mercury, or X boiling point 80 millimeters of mercury. That means that the boiling point was collected under vacuum. That is not the atmospheric boiling point. It's lower than atmospheric when it's under vacuum. You need to know the atmospheric boiling point of your alcohol. I'll tell you right now, they're all well over 100 degrees. So if you don't find a boiling point that's above 100 degrees, you need to keep looking, okay? Or we can help you in lab figure out what that boiling point is from the under vacuum boiling point, okay? Or reduced pressure vacuum point, or boiling point. But you need to know the boiling point of your alcohol so you can collect the proper fractions of your from your fractional distillation. Your lab manual tells you to collect 10, 20 degrees below that boiling point so you make sure you have all your alcohol, okay? So this fractional distillation can happen in lab this week, or it can happen in lab next week. You should have enough time next week to do it before experiment 11, okay? The simple distillation has to happen before next week. Now, after your fractional distillation, you're going to make a GC sample, which we'll have you do next week, of the alcohol, and you want it of the purified alcohol, and then you want an IR spectrum of your purified alcohol. So make sure after you complete the fractional distillation that you prepare the GC sample, collect the IR spectrum before you go on to experiment 11. And remember, be really careful with your product from this week. You need it for next week, so don't throw it away. So when you're doing all of these, the workup, all of your different layers, you're doing the distillation, hang on to everything till you know you have what you're supposed to have.